Watch a cruise ship pull into port sometime. Really watch it. This object, 16 stories tall, longer than 3 football fields, heavier than 100,000 fully loaded semi-trucks, glides toward a concrete pier with the quiet confidence of something that knows exactly where it is going. Passengers line the railing with their phones out. The dock crew waits below, and the whole thing happens in near silence, impossibly smooth with no visible drama whatsoever. Here is the problem with that scene. There are no brakes. Not figuratively, literally. A cruise ship has no friction braking system of any kind. No calipers, no pads, no mechanism that grabs anything and slows the ship down through resistance. The word brake, in the sense that you understand it from every vehicle you have ever ridden in, simply does not apply. And yet, the ship stops, every time, with extraordinary precision. So what is actually happening? The answer is not simple, and the closer you look, the more interesting the problem gets. Because stopping a cruise ship is not a single act, it is a layered engineering challenge that involves physics, propulsion architecture, and a fundamental rethinking of what it even means to stop something that has no surface to push against. Start with the physics, because the physics are not forgiving. A large cruise ship at cruising speed carries kinetic energy on a scale that most people do not intuitively grasp. We are talking about a structure that can exceed 100,000 gross tons, moving through water at 20 to 22 knots. That is roughly 25 miles per hour, not fast by highway standards, but applied to that much mass, the result is an object with momentum that makes a fully loaded freight train feel like a shopping cart. If you cut the engines on a large cruise ship completely and simply waited, the ship would coast forward for approximately a mile before water resistance brought it to a stop. A mile, with nothing running, just inertia and the laws of physics doing their patient work. That is the first thing to understand. Water resistance exists, but at these scales and speeds, it is a background force, slow acting, measured in minutes, not something you can use in an emergency. It is the difference between a natural stop and a controlled one. So, ships developed a different approach. The traditional solution is something called a crash stop. The logic is straightforward. If the propellers are pushing the ship forward, reverse the propellers and they will fight against the ship's own momentum. What this means in practice is that on a conventional diesel-powered ship with shaft-driven propellers, the engine reverses. The propellers begin spinning in the opposite direction. The ship, still carrying enormous forward momentum, continues moving forward while its own propulsion system pushes back against it, and eventually, over a distance that can reach 10 to 15 ship lengths for a large vessel, the ship stops. That works, but it comes with a hidden cost that most passengers never think about. On a conventional shaft-drive ship, the rudder works by deflecting the flow of water pushed by the propellers. When the propellers are running forward, water streams past the rudder and steering is responsive. But when you reverse the propellers for a crash stop, the water flow changes entirely. The rudder loses its effectiveness. The ship essentially goes blind to steering commands during the very moment it is trying to stop. Think about what that means. The captain has one lever to manage a crisis. Pull it, and the ship starts braking. But the moment that lever is pulled, directional control drops sharply. The ship can stop, or it can steer. It cannot do both simultaneously with full effectiveness. That is not a design flaw someone missed. It is a structural trade-off embedded in the physics of shaft-driven propulsion. And for decades, every shipmaster in the world understood it and planned around it. The ocean does not cooperate with clean solutions. Every stop is a negotiation between mass, momentum, wind, current, and what the engines can physically push against. And wind is not a minor footnote. A large modern cruise ship rises 8, 10, 12 stories above the waterline. Its broadside profile is enormous. In a strong crosswind, that profile acts like a sail. A headwind shortens a stop. A tailwind extends it. A beam wind pushes the entire vessel sideways during a deceleration that was planned for calmer conditions. Every stop is different. Every stop is calculated. Before every voyage, a ship's crew studies documented stopping data, measurements taken during mandatory sea trials before the ship ever entered commercial service. The crash stop test is a formal procedure. The ship runs at full speed, the engine is reversed at maximum power, and GPS tracks exactly how far the ship travels before stopping. That number goes into the ship's operational record. It follows the vessel for its entire life, and every captain who steps aboard knows it because, in an emergency, that distance is not theoretical. It is the margin between a close call and a catastrophe. This is where the story changes. The solution to the brake problem when it finally arrived was not to add brakes. It was to throw out the propeller architecture that made braking so limited in the first place. Azipods, pods, azimuthing propulsion pods, are electric motors housed in streamlined pods mounted beneath the hull. Each pod contains its own propeller, and each pod rotates a full 360 degrees on a vertical axis independently under computer control. This is not a minor variation on the shaft drive system. It is a fundamentally different idea about how propulsion should work. On a shaft drive ship, the propeller points in one direction, aft. The rudder steers by managing water flow. The two systems are separate and they interfere with each other under crash-stop conditions. On an azipod ship, the propulsion unit is the steering unit. The same pod that drives the ship forward can vector its thrust in any horizontal direction instantly without any of the mechanical constraints of a shaft and a rudder. What this does to stopping is significant. When twin azipods need to slow the ship, they can rotate to opposing angles, one pointing outward to the port side, one to the starboard side, while both continue running at full power. The thrust forces partially cancel each other's lateral components, while the hydrodynamic drag on the rotating pod housings adds additional braking force. Meanwhile, the ship retains full steering control throughout the entire procedure. The captain does not have to choose between stopping and steering. The system handles both simultaneously. Azipod-equipped vessels can stop in roughly half the distance of an equivalent conventional ship, with the propulsion system and the navigation system cooperating instead of fighting each other. This is where it starts to get genuinely impressive and strange. In 2022, ABB, the company that developed Azipod technology, introduced something called marine braking assistance, first deployed on Wonder of the Seas, a ship that at the time was the largest cruise ship in the world. The system works like this. In an emergency, the officer on the bridge presses a single button. The software takes over. It reads the ship's current GPS position, heading, and speed. It calculates the optimal angle and power output for each azipod unit to achieve maximum braking efficiency for those exact conditions at that exact moment. And it executes the entire sequence automatically, because doing it manually under emergency pressure, step by step, at exactly the right angles, with everything else also demanding attention on the bridge, is a task the system can perform faster and more precisely than a human can. A ship that weighs hundreds of thousands of tons can now execute an emergency stop by pressing a button. That fact should sit with you for a moment. If the way hidden systems get pulled apart and examined is interesting to you, the engineering beneath the surface of things that look simple, this channel is built around exactly that. Subscribe if you want more of it. But stopping is only half the problem, because stopping in open water and stopping at a specific pier, at a specific angle with controlled contact against a concrete structure are two completely different challenges, and the solution to the second one is different again. Here is the twist. Docking is not a stopping problem. Docking is a hovering problem. When a cruise ship approaches a berth, the goal is not to reach zero speed and stay there in some convenient location. The goal is to arrive at a precise geographic position, at a precise angle with controlled lateral velocity, essentially sliding the entire ship sideways against the pier. That requires not just forward and reverse thrust, but lateral thrust, applied with precision, continuously adjusted as wind and current push against the hull. Both thrusters handle the lateral dimension. These are propellers mounted inside tunnels that run perpendicular through the ship's bow, horizontal tubes that open on both sides of the hull, power them up, and they push the bow sideways, left or right, while the rest of the ship swings around them. Stern thrusters do the same at the rear, combined with the azipods, which can vector thrust in any direction. A modern cruise ship can translate sideways, spin in place, or hold a fixed position, all without touching anything. That last capability, holding a fixed position, is its own dedicated system. Dynamic positioning uses GPS data, wind sensors, and current readings, feeds them continuously into a control algorithm, and fires thrusters automatically to counteract whatever forces are pushing the ship off its target position. It is how cruise ships anchor at ports where dropping anchor is impractical or prohibited. The ship does not anchor, it hovers, perpetually, fighting physics with math invisibly below the waterline, while passengers ride tenders to shore and take photographs of the beach. The anchor, for the record, is not what most people imagine it to be. It exists. It serves real purposes, particularly in preventing a drifting, disabled ship from moving further toward danger. But it is not a brake. A ship traveling at any meaningful speed cannot safely deploy its anchor as a stopping mechanism. The forces involved would be catastrophic. The chain would not survive. The anchor is a last resort position holding tool, not an emergency deceleration system. There is something philosophically interesting buried in all of this. Friction braking, the kind used by cars, trains, bikes, and nearly every other vehicle on land, works because there is a surface to push against. Rubber grabs asphalt, brake pads grip a disc. The vehicle's kinetic energy converts to heat through that contact. But the ocean is not a surface. It yields. It flows around the hull. It offers resistance, but resistance is slow and passive. It does not grip. So the engineers who built these ships could not borrow the solution from land vehicles. They had to solve a different version of the problem from scratch, using only what they had: propulsion. The same force that accelerates the ship would have to decelerate it. The same system that steers would have to stop, and the same pod that cruises at 22 knots across open ocean would have to rotate 180 degrees and push back against several 100,000 tons of momentum without losing steering authority in the process. That constraint is what produced Azipod propulsion. That constraint is what led to algorithmic braking assistance controlled by software and GPS. That constraint is what turned a simple engineering problem, how do you stop a big boat, into one of the more elegant solutions in modern maritime design, not in spite of the limitation, but because of it. Go back to that image of the ship gliding into port, the passengers on the railing watching the dock approach, the quiet, unhurried smoothness of it all. What is actually happening in that moment is this: rotating propulsion pods beneath the hull are vectoring thrust against the ship's own momentum. Lateral thrusters are nudging the bow toward alignment with the berth. GPS is tracking position to the meter. A pilot, a local maritime expert who boards the ship specifically for this maneuver, is coordinating with the engine room and the tug operators standing by. Mooring lines are being prepared. The entire approach has been calculated in advance, with the ship's own documented stopping characteristics in mind, adjusted for current wind, current water conditions, and the specific geometry of this particular pier. The captain and the pilot are not driving the ship. They are conducting it. Every input is deliberate. Every thruster is calculated. The smoothness is not a product of simplicity. It is a product of complete, total, deeply engineered control over a physics problem that has no easy solution. There are no brakes because the ocean offers no surface to brake against, so the brake was built into the propulsion itself. The thing that moves the ship is the thing that stops it. The steering system and the stopping system are the same system. The visible product of all that invisible engineering is a 16-story structure settling silently against a pier with the patience and precision of something that knows exactly what it is doing. It always did. It was just operating on a different set of rules than you assumed. I hope you enjoyed the video and learned something new about one of the most fascinating engineering marvels ever built by mankind. If you want more content like this, please subscribe and hit that like button. I'm Larry, and this is the Ship Files. Thanks for watching, and I'll see you in the next one.